I'm Gabrielle. I'm going to be doing part B of homework 1. So the problem statement is divide the CSDRs into 20 smaller CSDRs in a series to mimic a flow reactor with backmixing. So this CSDR is going to be very similar to the one that we did in part B. Part B up here. So we're going to simulate a plot and the concentration of the temperature evolution for 20 tanks over 2 minutes, starting with a concentration of 0.5 and the temperature of 338.5 Kelvin in each tank to maintain a constant inlet concentration and temperature of 1 mole and 338.5 Kelvin. Qualitatively explain the qualitatively explain the concentration and temperature profile. So this is going to be very similar to part B, so we're going to use the same code as part B and just kind of modify it. So the first thing that I wanted to do was I want to change this to N, so our number of tanks is going to be 20. Things that I want to take out, this, it's really not needed anymore. I'm going to take out this and I'm going to redo it down at the bottom. This is our V here, is going to be our total volume. So our volume is going to be split up into 2 different tanks. So I'm going to have just V is going to be equal to the total volume divided by the number of tanks. And then this internal energy is going to be divided by N because it's going to be split up for each tank. So N as well. Our QC is going to be changed to 300 Kelvin. And then our CAO as well can be taken out. So I'm going to change these. So the first thing I want to do is change to T0. Is going to be filled for each tank, right? Because we're at a steady state. So this is going to be from, I think this is in parentheses. When we do fill, we do parentheses. So it's going to be from N, and we're going to do, so our temperature that was given to us is 338.5 Kelvin. 338.5. And then our C, so our concentration not is going to be NP full as well. And this is going to be number of tanks, and this is going to be the 0.5. What that we have next is, so our concentration, we filled it up for each tank. So every single tank is going to have that. And the next thing that we want to do after this is we're going to make our vector knot. So our vector knot is going to be kind of something that we use as our guess for ourselves. So it's going to be RP. We're going to concatenate our 2 functions that we did, and we're going to do concentration first because because when we unpack our vector in our definition, it's going to be CA naught, so CAO and C naught for our temperature. So these are the things that we wanted to add and change with our new thing. So let's do Shift Enter on these. Shift Enter, Shift Enter. See if there's anything needs to be fixed. I think it's fine. Oh. Oopsie. Okay, so our right-hand side, the things that we want to change about this is our vector. I actually want to split the vector. So I do np.split and vector, and I do 2. Okay, so our K equation is going to stay the same. But the next thing that we want to do is we are going to do a concentration change, right? Like our ODE that we did for part C. So and it's going to be from 0 to 20, right? So we're going to do the same equations. So I got here to pull up these equations. Okay, and so we're going to change some things about this one. So the first thing is we want to change it to CA. All these C's go to CA. But what the difference between part C was to this one is that there wasn't any chemical reaction happening. There was not a consuming of A to become B, but this one is going to. And that's why we're going to do a concentration at time 0 multiplied by our concentration at time 0 as well. This is going to give us our rate of reaction. So time 0. And then it's going to be the same thing for this one as well. The change in concentration from the first tank to the nth tank. So, this is going to be from, 1, so the first tank to n. And then the Ca here is going to be from the concentration of the first tank to the nth tank as well. Okay, and then the next thing that we want to do is we want to have a change in temperature. So the change in temperature from the first tank, so from the 0 tank, so d T naught equals, and we're going to use this equation that we already had for it, so, and we're just going to change that one around. Okay. So, I'm going to change this T to undercapitalized. So our T naught is actually going to be our Tn. Our T naught is going to be our Tn, different from the one up there. And this is going to be at time T. That's going to be different. And then we have this here is going to be at the temperature at the 0 tank. 0 tank. And this K here will also be at the 0 tank. And then we have our concentration at the 0 tank as well. And then we have our T is going to be at the 0 tank as well. And then I'm going to make this one here. Okay. So then the next one that we have to do is going to be our dT to our change in temperature from the first tank to the end tank. So let's do that. First to end. Okay. So we're going to change this one to just T. And this is going to be different. So this one is going to go from our 0 tank our 0 tank to our last tank, to our second to last tank. So this T is going to go from our 0 tank to our second to last tank. So it goes from this minus 1, and then that here, and then I'm going to change this one. So this one is going to go from the tank number 1 to our nth tank. So then this concentration down here, well, our concentration in our K constant is going to be from 1, so the first tank number 1 to n. And then our concentration is going to do the same thing, so tank number 1 to n. And then this temperature down here is going to go from 1 to n as well. Okay, so then I'm going to take this out here. So what we're going to return is we're going to actually concatenate all of these together. So the first one we want to do is BC not BC1 okay, then BT 0, T0, and then BT 1 through N. Okay, so that is going to be for this one. And then before this, we're going to actually define our two CN. So we're going to define CN, T, and we had this as what was going into it was 1. And then we're going to define our TN to return 338.5, which was given to us. So Control C, Control C. Okay. Now the next thing that we want to do is this is going to be 2 minutes long, so we're going to change our TN to 2. And then we have our solve IDP. We're going to change our guess from, the CA naught to the TA naught. We're going to change that to the vector naught that we had made in the beginning. Vector, I think I'd put a 0 for that one. Vector naught. Okay. So then here, our t-plot is actually going to be, we're going to change that, but everything else should stay the same on that one. And then we're going to actually, split these, right? We're going to split resolution t-plot, right? And then we're going to do 2. And then this is going to be on the axis of 0. And then this is fine because it's going to be 2 graphs. And then we're going to do a for loop. So for I in range, and we have 20 tanks, so we're going to put n. And then we're going to do this. And then, no, I don't want that. I want to go here and tap that over. Okay, so this, the first one we want to do is we want to do our concentration. So it's going to, we need to do our C, we need to do a separate plot for that actually. So we're going to do our C plot and our T plot. So, I guess C plot first. C plot is equal to, so instead of this here, I did that wrong. It's going to be, you're going to have a C plot, is how we did it. We did C plot here, and then we did temperature plot here. So that is what we changed. So now we have our concentration plot, and then our temperature plot. And then we have, so sorry for that noise, that's my cat again. Anyway, we have our concentration plot, and then we have our temperature plot, and those are being split and solved with our T plot. Okay, so now we can go down here and change this to C plot. So this is going to be our C plot, and this is going to go from the iteration that we're doing. So this is going to be the first one, and then I wanted to change this C and function C and then I. And then this is for T plot, I and the current iteration, and then 2, and then I wanted to change this to F. And then I need to put this in the for loop as well here. Let's see what this is. Okay, I'm going to actually change the height of this. So weird. Okay. Okay, so here we have our plot. So this plot over here is our concentration plot. And so let's kind of see what it's doing. So we have down here is our temperature. So it's going, sorry, time. So it's going from 0 to 2 minutes, right? So this is starting at 0.5, and then the concentration is kind of shooting up and then stabilizing around 1. And then you can see, and this is the first tank, so you see a not tank. And then we have our second one, and you can see how each tank keeps getting less and less concentration, and that's because we have a reaction. So the reaction is it's consuming our concentration of A. So it is going to get less and less concentration of A as the tank goes further, because there is going to be more chance for that chemical reaction to happen. That makes sense. And then let's look over here at our temperature. So our temperature, again, we're going from 0 to 2 minutes. So we have our first tank here is kind of having a steady temperature, but you can see as the tanks go on, you're kind of having a little dip. Starting out with a little dip and then it goes up, and then little dip and it goes up, and like bigger dip with the longer you get down through the tank. So this is happening because when we're having a liquid in there, in these tanks, the temperature is dropping the longer it's being in this tank. So the longer it goes into these tanks, so the longer it's through all of the 1 through 20 tanks, it's going to get a lower temperature. But since this is an exothermic reaction, what's happening is temperature is being released. So when you're having these chemical reaction and the chemical reaction happens, the temperature is going to shoot back up. So it's going to shoot back up on here. So this makes sense. So that is the end of part D.